Good morning, and thank you for your warm welcome. This is my first time in Poland. Just arrived last night and had a very enjoyable time going to dinner with some of you and just walking around the streets. It was very fascinating because from the U.S., Poland seems so far away. It's like on the other side of the world. It's like on the other side of Europe. And just so growing up, it was just, I heard stories. We'd hear about the great wars and Poland's involvement and things that happened so far away, and just walking the streets, places I've only heard about in the history books, was just very fascinating last night. And so thanks for the welcome, and I'm really excited to be here. I'm going to start the talk today with a little bit of historical perspective from the networking perspective, because I think it's worth looking at sometimes why are we where we are today? How did we get here? And so I'll be doing some of that as I start my talk about IPv6. The organization that I am with is part of the U.S. Navy, and I have been there all of my life. And it's a laboratory. It's not a military laboratory where there's like lots of military people around. It's a civilian laboratory, so it's mostly scientists and engineers that develop technology that might be useful in the Department of Defense. And some of the things that are done at the place where I work, examples like we were involved in building the bathyscaphe that went to the deepest parts of the ocean many years ago, the Trieste, down 7 miles to the bottom of the ocean. That was built at our place. A lot of other underwater vehicles. The dolphins that are trained to go and retrieve things from the bottom of the ocean. I can see them out my office window. They're done right at our place. Some of the earliest experiments in fiber optics communications were done at our laboratory. It's just in the offices right below mine. And so it's just an interesting place where there's a lot of history and a lot of science that has gone on in that organization. And so it was appropriate that we had been doing some of the earliest networking as well in the late 60s and early 70s. So the things I'm involved with a network called the Defense Research Engineering Network, which is the DoD ISP for the research and engineering networks and organizations within the U.S. Department of Defense. But I'm also part of an organization called SPAWAR, Space and Naval Warfare Systems Command, which does information technology, communications, and other things for the U.S. Navy. And I'm the security manager for that organization. Also, I've been involved in the Federal IPv6 Task Force for the last few years as the U.S. federal government is trying to deploy IPv6 to all of its agencies. And that's been a monumental, and there's been a number of successes that I will talk about today. So let's start with some of the history. And going back to when I was first hired by the Navy as a young scientist, back in 1976, there was this thing called the ARPANET that I had not heard about until I actually came and worked for this organization. And it was the type of thing where this was the era of the mainframe computer, or any research organization would have a mainframe computer. In the 90s, a research laboratory wanted a supercomputer, but decades before that, it was just to have one computer at all. And they were usually large IBM, UNIVAC, other types of mainframes, and they were expensive, but they needed to be shared. And so researchers that wanted to reach across the country to talk to other large research computers needed a network. And circuits were expensive, they were unreliable, and so there was development into network switching, packet switching, and ARPANET was one of the places that happened. So when I first was hired, they took me to this back room and they said, see this box? And it looks like the picture up there, that's an IMP. It's supposed to allow us to connect our big computer to the network. So go figure out how to do that. And so there was this large box, and that was the IMP. But then there were large boxes next to it, very large. Those were the modems, 56 kilobit modems, huge racks full of equipment just to do 56 kilobits over those old circuits. It was all analog. Excuse me. The protocol was something called BBN 1822. They handed me the manual and said, figure out how to make our UNIVAC computer talk to this. And then there was something called the network control program, which interconnected the hosts and the IMPs and then the IMPs to each other. Later, TCP/IP came before the days of TCP/IP. But I want to point that out because we actually ran both protocols for a while. There was the NCP program, there was the TCP/IP program. And so we didn't call it dual stack in those days, but it really was dual stack, running two protocols on the same network. So I bring that up because in IPv6 discussion about you run dual stack as one of the transition mechanisms. In 1983, we turned off NCP. This was announced a year in advance. We said, we're transferring to IP, we're going to turn off NCP, and it was a great incentive for everyone to implement IP, which was IP version 4. The applications in those days, there weren't very many. Telnet, FTP, and email. And the routing for IP, you wrote your own router code. Cisco didn't exist. None of the other router vendors existed. And so what you did in your PDP-11 or other microcomputer, whatever you had laying around, you went in and wrote your own router code. And it was fairly simple in those days. In those days, we didn't call them routers or routers. We called them gateways. The name changed over time. That's why you have the G in EGP, Serial Gateway Protocol, or BGP, Border Gateway Protocol, because we called them gateways in those days. If we called them routers in days, then we'd have those protocols would have been ERP and BRP, ERP and BURP. Might have been interesting. Addressing, NCP used 8-bit addresses, and they took the 8 bits and they broke it into sections. The first 2 bits were the host number. The last 6 bits were the site number or the node number. And the reason for 2 bits for host is because in those days, no one could envision any organization having more than 4 computers. Because typically, if you had a computer, you probably only had 1. And if you were really advanced, you might have 2 or 3. Because they were computers that cost millions and millions of dollars, and it was usually a very large mainframe. The one room that we had was a very, very large room for the computer, had just 1 computer. Because even memory modules took whole racks of space, very large disk drives. If you had a 300 megabyte disk drive, that was very large, and you had many, many, many of them. So it just took a lot of space. So you didn't have very many computers. So 2 bits was enough. And the way you wrote it was host number / node number. So my address, since I was node number 3, was 0/3. And but you could shorten it to just 3 if it started with 0. So my address, I could just say I'm 3. That's my host address if you want to connect to me. With IP, it's 32-bit addresses, split as a network part and a local host part. And it comes in 3 flavors, or at least in the early days, A, B, and C, depending on how big your local address part needed to be. And it was written with dots, as you know. ARPANET was network 10. After ARPANET was shut off, network 10 was available and eventually became RFC 1918 space. So it wasn't always private address space. It was the ARPANET address range. CIDR didn't come till much later. We used the A, B, and C addresses for many, many years. And so this is also interesting, just seeing the nomenclature. So in NCP, we went from slashes as a separator to IP periods, IP version 4. Now with IPv6, colon is a separator. So seeing a lot of different versions there. Here's what ARPANET looked like when I first joined in July of 1976. And I am right there where it says Naval Undersea Center, NUC. That was my node. And so we had the link going up to UCLA, that was node number 1. I was node number 3. So that's what it looked like when I first joined. So I wasn't there at the very beginning, and the network was already operating, but it was before it ran TCP/IP. So looking back at some of the history, some of the dates which you might find interesting. So 1969, the 2 great events in the world. We landed on the moon, and the first login via the ARPANET much later. This was the case where the person doing the test was typing LOGIN to log in and got the L across and it got the O, but when he typed G, the whole thing crashed. But that was at least the first remote login via the ARPANET. In 1976, when I joined, there was about 100 hosts on the network. On all of those nodes, remember, each site only had 1 or 2 hosts, maybe 3. And so there were only 100 hosts in the entire network. But by January 1983, NCP was turned off because everybody had to use IP, and it was a very strong incentive. And so compare that today, how long it's getting us to try to get to IPv6, because there is no immediate incentive. Nobody has yet said we're turning off IPv4, so it's taking a long time. In 1983, I had my first break-in. Somebody broke into one of our computers. It was a password guessing attack from another university, actually UCLA. And in those days, before then, nobody worried about security because it was a totally trusted community, mostly the U.S. military and a lot of universities. And so you didn't worry about setting passwords. Or if you did, maybe it was the same as your login name or something. I think what he guessed was user ID Jones, password Jones. I mean, something like that. It was very simple because you just didn't worry about it. So this is when I became involved in security on networks because of our first break-in. 1984, we got DNS. Before then, we just had host tables, and you would download them once a day, once a week, once a month, depending on if you needed to talk to somebody and you needed to know their address. You just update your host table, and you put it in etc hosts on Unix or appropriate file on other operating systems. And then in 84, we had also Ethernet starting to pop up. And when you wanted to do Ethernet in those days, you'd order your 300 feet of yellow cable and run it through your building and put in the vampire taps and hook it to your PDP-11s and VACs and other computers. But what we found in a laboratory like ours, our research group had an Ethernet. The one up at the top of the hill had an Ethernet. There was another group down the way that had an Ethernet, and they all wanted to tie together. So you had to give each one of those its own address range. But you didn't go back to the NIC in those days and get a new block. What you did is you took your existing block and started breaking it into pieces. And so subnetting happened. And the ideal address space then, in those days, was the class B, which today is a /16. It was ideal because you could break it into lots of subnets where a class C you could not, and later they didn't give out class A's anymore. Although I did have a class A, I had network 27 for many years, but I did give it back because it was we were starting to need the addresses elsewhere. So class B's were in high demand because they were subnetted, but then we ran out of addresses. So in the early 90s, if you went to the IETF meetings, the big conversation was, we're running out of class B space. But a couple things happened. They came up with CIDR in 1993 time frame, classless interdomain routing, where we got rid of this class notion and carried along a subnet mask along with the addresses in the routing tables. Before that, there was a thing called variable length subnet mask, VLSM. That was the terminology. Later, it was formalized as CIDR. And then, of course, there was NAT as well. I don't put NAT on my slides because NAT is evil, and so we don't like to acknowledge that. 1994, there was the next generation IP working group because we knew we had to do something. IPv4 wasn't going to live forever. The IPv6 first spec was 95 and then revised in 1998. So that's when IPv6 really started. First implementations, 98, 99 time frame, and then big deployments starting in early 2000s. And today, 15, 16, 17 years after that, we're still trying to deploy IPv6, and we're not there yet. If you look at the utilization charts, we're at like 1%. So why is this taking so long? Why do we need to do this? Is it going to succeed, or will IPv6 just die? Or is it our next big crisis? That's what we'll talk about today. So where are we today with IPv6? It is not fully matured in all areas. There's still some pieces being worked out. But it is ready for prime time, and there are a lot of people using it in production, on production networks. I mean, even Google is using it. So that it is important, it needs to be deployed, and many are trying to do that. Security and performance of IPv6 is equivalent to IPv4. That was a lot of the earlier studies being as secure and perform as well, and it's pretty much been proven that it is equivalent. The deployment does not have to be costly. People worry about how much money do I need to deploy IPv6? Is it going to cost millions of dollars? And we see even in the U.S. government that some groups researched it. They thought, oh, I need to replace all my hardware, I need to buy all new routers and other devices, and so it's going to cost millions or billions of dollars, and there was actually some request to go in to do that. Actually, what they were doing was they wanted to replace the hardware anyway, and they were just using IPv6 as the excuse. It really doesn't have to be costly if you use normal technology refresh cycles of 5 or 6 years to make sure anything new that you buy is IPv6 capable, and you get a vendor commitment that if it's not delivered right away, it will be delivered or you'll get your money back. And so as long as you do something like that, you'll be safe. If you haven't started yet, you're probably too late, because these cycles do take 5 to 6 years. So if you haven't started and you'll be forced to upgrade, then you will have a major expense. And so the sooner you start, the better. Some of the suppliers have limited IPv6 support, but it's getting a lot better. All the major operating systems are in pretty good shape. The switch vendors and the router vendors are all in fairly good shape. There's places where home networks on cable modems or DSL lines, some of those ISPs are not V6 capable or enabled yet, but that's coming along fairly quickly, especially after World IPv6 launch that we had earlier this year. There's a larger commitment to the cable operators, and that's really, really helping. People ask me about what's the business case for IPv6, because typically if they're in an organization and they need to get resources or get people working on deploying IPv6, manager will say, well, what's the business case? What's the return on investment? I want to see that it will be good for the business. I will make more money. I will be able to do things cheaper or whatever. And people that spend a lot of time trying to come up with a business case usually fail because there's not a near-term return on investment where something works better. You know, they look for what's that killer application that I can't do, or what's that website that I can't get to today that I'll be able to get to with IPv6. Well, there isn't one. So it's a business case. Really, the business case is it's a longer-term thing. It's important for the survival of the internet, and if your business is not embracing IPv6, it will die because your competitors will sell IPv6 when it is in really high demand. So the business case is business survival. You will not survive if you're not deploying IPv6. And then the killer app, people say it would be nice if there was a killer app like the web was for the internet. You know, is it gaming? Is it video distribution? What's the killer application that's just going to make everybody demand IPv6? And it really isn't there, because the killer app is the internet itself. The internet cannot survive unless we have IPv6. We can't deploy new devices. All the new mobile smartphones, they can't get addresses, and so they have to do IPv6 only because they cannot do it with IPv4, which forces them to translation, which means it's going to break the internet, which means lots of bad things happen. So it's for the survival of the internet that we need IPv6. The urgency, there's a quote from John Curran basically saying, all you content providers, your websites need to be dual stack very soon. We're out of addresses. Last year, IANA, the global pool, ran out. Then Asia and Europe have since run out. Europe just recently in September. The growth and security of the internet is at stake. And I say growth because it cannot grow. We're out of addresses. The security is at stake because there are things that are happening today because of deployment of translators, which can break some of the security, both the carrier-grade NAT type of translators, which law enforcement people hate because they can't find the bad guys anymore, or it's very expensive because of all the logging you have to do. But also you can't deploy things like NAT64, DNS64, because that might break DNSSEC if it's in the path. And so there's a lot of security implications as well. So we need to complete this transition quickly. There's an urgent need to V6 enable the public internet soonest. Because if you think about it, if the public content is all dual stack, then the client base that's out there, new devices, mobile phones, home computers, if they have only IPv6, they'll still be able to get to the public internet, at least all the things that are important. So there'll be a place sometime soon where we'll reach critical mass on all the public content. It'll be IPv6 enabled, and then you, with your client, home computer, smartphone, or whatever, can live just fine with only IPv6. And then the stragglers that haven't converted yet will just no longer be part of the internet, literally. And so another reason why it's really important for you to V6 enable your public-facing services. Mostly worry about the web, your authoritative DNS, and your mail exchangers today. That's what's really important. And it's actually fairly easy. In most cases, you can just turn it on as long as your ISP can deliver it to your doorstep. Now, the U.S. federal government, we've tried over the years to do mandates. The first one was in 2003, saying within 5 years we want all our networks to be IPv6 enabled. And as we came up to the deadline in 2008, there was a reporting that was required from all the agencies to demonstrate that they were IPv6 ready. And what they did was they would take a couple of their routers in their network, they would enable IPv6, they would do a ping test saying, we can do IPv6, and then they turned it off. And so it was not successful because it didn't result in IPv6 enabled networks. And so in 2010, the Chief Information Officer of the U.S. federal government said, we are really going to go to IPv6, and we have 2 years to do it. So the deadline was this past September, just last month. And all public content needed in the federal government needed to be IPv6 enabled. And then within 2 years, 2 years from now, everything internally that needs to talk to the internet needs to be IPv6 enabled. And the previous mandate didn't work, like I mentioned, and there was to make sure that this really happened, there was a federal IPv6 task force that was put together. There were transition managers in every so there's been a team pressing hard to deploy IPv6 in the federal government. The status today, this is a public website. You can go and track the status. There is, on the left, you can see for every major agency, and these are large bureaucracies. I mean, some of these organizations are well over 1 million people. And you can see nobody is all green. You can see that over time, a lot of people waited kind of till the end. You see the uptake, but then about the time after the mandate hit at the deadline, it went flatline. So that's also a concern. What happens in the future? What's the incentive for the ones that didn't make the deadline? But at least 36% have been completed, but we do have a ways to go. So the question would be, is it a success or was this a failure? So how much of the change came right before the deadline, or why did much of the change? People seem to procrastinate, or they have, for the first year, almost nothing happened. And then finally they said, oh, this is real, it's really going to happen, we need to start working on it. And by then it was, my ISP doesn't support IPv6, or my firewall doesn't support it, my router doesn't support it, I need to do code upgrades. And so then they had to work over right up to the deadline. And then at the end, there was a real uptake as people turned it on. So the metrics only show 36% completion. Does it indicate a failure to meet the goal? It seems like at face value that would be the case. And if you saw the press reports in September, they were all saying huge failure for the administration because they only got 36%, or it was only 35, 34 at that time. And so it's really bad that they didn't succeed. But I think there's a different story to that. Also, after the deadline, what incentive is there to leave it turned on or to even continue working on the other 64%? So that's the burning question. So success, yes, it was huge, I think, because when you have the entire federal government saying to industry, I need IPv6 and I need it now, I've got a deadline coming up, that's a huge incentive to industry to actually finally deliver it. Before then they were saying, nobody's asking for it. Nobody tells us they need IPv6. You'd go to a conference or something like this, you talk to the vendors outside, and when are you going to have IPv6? Nobody's asking for it. All they care about is getting to the next quarter. When you have the entire federal government, multiple agencies of millions of people saying, I need it now, they can't anymore say nobody's asking for IPv6 because there's a huge, huge demand now. Also, there's a huge awareness in the federal government for what IPv6 is, what it's needed for, what are the mandates, and there's people holding workshops, going to training, working with the providers, and so there's a lot more energy into IPv6 and learning about it. So that's huge as well. Also, a lot of our government content is now IPv6 enabled, so citizens and others that need that information can do that over IPv6, and that's really important. And so we feel we're being part of the solution rather than part of the problem, because before then, governments, sometimes very slow to deploy things like new technology, are are the slowest, and so instead of being part of the problem, it's part of the solution. But it also sets an example for many others and really paves the way for the public, for the rest of the public sector. Also, we really, really hope this is an incentive to other governments, maybe like your own government, do something similar. See what worked here, how well it worked, what lessons you learned, and I hope all governments around the world do something similar, and many are. Many were even in before the U.S. did it. And so I think that would be really good for you to work with your own government to try to take some of these lessons and apply it internally, because it's going to take time, maybe a couple of years, and it's better to start sooner than later. So carry that message forward. So some of the lessons learned. Number one, you have to gain operational IPv6 experience before putting too much effort into enterprise-wide planning. We've seen a lot of people make the mistake of spending a year doing planning and then they got it all wrong. So it was a wasted year because they're going from IPv4 experience, and that's a waste of time because IPv6 is very different in things like addressing and worrying about transition mechanisms and various other things that you really need to rethink that from scratch, and that only comes from operational experience or bringing in some experts. With addressing plans, everybody gets it wrong because they're all making the same mistakes. I have a list of that in just a second. Another lesson is go native. Try not to use translators, tunnels. Use dual stack. Also, start from the outside and work in. We found that's easier for a lot of folks because if you have a firewall, and especially if you're under government mandates to lock things down a certain way, trying to get IPv6 through that firewall can be challenging, especially if it's not ready to support it. But if you're working from the outside, your public services, like your public website and so forth, they're typically, you're not worried about confidentiality. The worst thing you're worried about is the denial of service attack. And so it's less risky in a certain sense because it's usually outside the firewall, it's maybe out on your DMZ, and it's a good place to start. There's going to be challenges and surprises, and you don't know those until you start. So another reason to start early and start small. Try a few things, turn it on, and you will learn along the way what else you need to do and what needs to be replaced. It's just a very good way to do it. And it doesn't have to take a lot of resources if you start early and use Tech Refresh. So as we look forward in the federal government, what's the incentive? How do we keep the pressure on to have all those agencies, the ones that miss the deadline, to actually continue their efforts? Well, the current plan that's being discussed in the federal government is we are not going to allow organizations to renew their .gov domains if they are not IPv6 compliant, and maybe if they're not DNSSEC compliant. So when they come around to renew their domain, you want a domain. If you're not IPv6, come back to us when you fix that problem. And I think that's going to be a huge incentive for a lot of folks. So hopefully other governments and top-level domain providers are thinking something similar as well, because that might be the thing that really motivates folks. Some of the keys to success, very important, the information official in your organization, the CIO or whatever it is, needs to set a clear vision and a mandate with deadlines. If that doesn't happen, you cannot do it from the bottom. Your network engineering group cannot get all the applications converted. They can't deal with the public affairs office to get the public website converted. They're not interested. It can't be driven from the bottom. It's got to be done from the top. And you have to have responsibility at the right levels. You need to publicly report status along the way, like the charts I showed you a few minutes ago. Make them public. Compare with how everybody's doing. It's very important to tracking. We found in larger bureaucracies, many have outsourced their IT staff and all their IT work. They're just part of large contracts to support their networks. Those people don't necessarily have IPv6 expertise. Rely on them for doing so because they'll probably steer you in the wrong direction. Bring in other experts that know about IPv6. Interact with your service providers soon and often. Tell them why it's important, and then insist that anything they deliver to you is fully IPv6 enabled and capable. Don't do anything new unless it supports IPv6. And tell them you'll switch go to their competitor if they don't provide it, and that's very useful. And then, of course, key is having dual stack support from your ISP. So if you're an enterprise, an organization, if your ISP can't deliver the IPv6 connectivity to your doorstep, that's a real problem. So put pressure on your ISPs, and if you are an ISP, then be ready for when the demand hits. So don't wait until customers start asking, because it'll take you a few years to build it out. Addressing plans, common mistakes. For some reason, if you're mostly doing IPv4 and you start doing IPv6, a lot of people don't do /64s for the subnets. They do a 120, or I've heard of 118 or whatever. It's like, why are you doing this? And it's, well, you know, in the Class C days, we had 8 bits for host, and so I assume we need 8 bits for host in IPv6. I'm like, no. It's totally different. You have to unthink everything you knew about IPv4 addressing. You don't have to be conservative. And people just can't get their mind around it because they've been being conservative for so many years that the idea of using these large chunks of address space, it just feels wasteful, and they can't bring themselves to do that. So read the RFCs that are referenced here. Also, people think that the addressing plan has to be perfect the first time because they can't afford to readdress. That is wrong thinking as well. You will get it wrong the first time. You'll probably get it wrong the second time. I've seen everybody, it takes at least 3 times to get their IPv6 addressing plan right. And just a plan on readdressing. So start small, and once you learn from that, new addressing plan, deploy again to a much larger environment. You'll learn some new things, and then you'll realize, oh, I could have done this different, I could have done that different because of large address space, and then you'll get to your third plan. Also, you no longer have to wait for organizations to say, I need this much address space, and then go to a central agency to figure out how much to allocate, because you know the answer. Sites get /48s, and so you can pre-allocate everything, and it saves a ton of time. And people can't get their minds around that either. And also, it's more subnet-centric than host-centric, so you don't count hosts anymore to determine subnets or anything like that. You count subnets. And so look at your physical topology today. How many subnets do you have? They each get a /64. How many sites do you have? They each get a 48. You're done. So it's really that simple at the highest level. Said that already. Okay, some do's and don'ts. How am I doing on time? Is anybody watching? Okay, so some do's and don'ts. I got a couple slides on that. Things to do: get buy-in from your corporate leadership, your CIO. Develop a corporate culture. So everybody in the organization, especially if you're a development organization or a research organization, anything new you build, buy, deploy, any new initiative must be done the IPv6 way. Consider IPv4 as this legacy thing that you also support, because the primary way is IPv6. Recent example in our own organization, we had a large video conferencing system, and we decided, oh, we're going to get something brand new, and went around to different providers, and we happened to, end up choosing the Cisco telepresence stuff, but it was because they said they could do IPv6, and they guaranteed that it would support it. There was some history with Canberg and others that it could be supported. So bought all new hardware, and what did we turn on first? IPv6. It had to work with IPv6 first, and then we provided legacy support for IPv4. If you do it the other way around, you'll have to do an upgrade later. Why go through the pain? Do it the IPv6 way first, worry about legacy later, and then it's going away anyway. So don't put a lot of energy into it. Take baby steps, do the low-hanging fruit first, get experience, use sort of the spiral development approach. Leverage technical refresh. You don't have to spend a lot of money on forklift upgrades that way. Start now. If you haven't, you're too late. Public-facing services first, go native, avoid translators, and choose suppliers with a good IPv6 story. Oh, and a word on that. What I use in my office is I get a lot of companies that come and say, I want to give you a presentation on my product. I've got a great product. The first question I ask them is, well, do you do IPv6 in your product? Because we have an IPv6 network, and we want to make sure everything we buy is IPv6 capable. And they'll say, oh, yes, we do IPv6, and here's on our brochure. The next thing I do is I said, okay, wait a minute. I'm going to your website. I can't reach it over IPv6. Oh, yeah, we haven't got to that yet. Well, then you don't have a good IPv6 story. Call call me back when you have that fixed. Have a nice day. And it works. And I even have it to the point now where the administrative staff in our office, the secretaries that answer the phone, they do that screening for me now. So there's a gateway for the vendors that come in and want to sell me something. They know the right questions to ask. They go to the website and make sure you can reach it with IPv6. If they pass those, okay, then they can come talk to me. Otherwise, don't call me back until you fix that. It's really great as a filter. Because think about it. A technology company is probably an advanced technology company if they are looking towards the future and are actually working on it and have a good story. If they don't, it's probably not something I want to look at anyway. It's a waste of time. They're not in the mainstream. They're not a leader. I want to look for the leaders, and a good indicator is whether they're doing IPv6 or have a good story. Some of the don'ts: don't waste a ton of time developing a complete IPv6 transition plan for a large organization. Start small, turn some things on, learn from it, use the spiral approach. Don't base your addressing plan on anything IPv4. It's a new ball game. Consider the first one a throwaway, maybe the first 1 or 2 addressing plans. It's a throwaway. You're going to readdress anyway, so just have that mindset. If you're spending more than a day on your first addressing plan, you're wasting your time. You know, most plans, if you know what you're doing, can be done in a few hours. Business case we talked about. And don't be afraid to break some glass. I mean, if you turn IPv6 on your website, what's going to break? Only like less than 1% of the world out there is going to try to reach you over IPv6. So at worst, less than 1% of the world might have a problem if you did it wrong. It's a lot better to do it now than wait till the world is maybe 50% deployed, because then you'll have 50% breakage if you do it wrong. So some other observations, other news, random things. There was this thing called World IPv6 Launch. Now, in my organization, we weren't directly involved because we have this saying that it's like every day is IPv6 day for us because we've been running this stuff for over a decade. We first turned it on, I think, in 2001 on our production network, and websites and a lot of the services just have been turned on for a long time. So what World IPv6 Day for the rest of the world we had been doing for like a decade. But the thing that was different about us is our internal network, all the laptops and printers and servers and everything internally is fully IPv6. So at a desk, if they try to reach the internet via the web or whatever, they're going to try IPv6 first. And so when the world turned on IPv6 through a lot of the content providers and other places, we would see a lot more content that we could reach over IPv6. So the percentage of traffic would go up, we thought. And so we wanted to observe whether this is the case as an observer. And so we've been watching this for a while. Now in 2009, before Google did any whitelisting or any IPv6 at all, we were about 1%. 1% of our traffic was IPv6. After we had Google whitelisting, it went up to 2.5%. When YouTube was turned on, it jumped to 10%. So things like streaming content has a huge impact. Others have noticed that, like the home users, when Netflix went IPv6, IPv6 load went way up. After World IPv6 Day, that was last year's event, it was 15%. This year, after World IPv6 launch, it went up to 20%. And you can kind of see the graph there, how we're doing today. Sometimes it jumps up to as high as 60%, but mostly it averages around 20% for the day. So it definitely made a difference in impacting how much of the traffic is over IPv6 as we observe it at our border, traffic coming into our site. So it's not about how many sites are IPv6 enabled, it's how much content comes from those sites, be it streaming or whatever. And so that's why a huge jump with Google and YouTube. So the top challenges I see in an enterprise deployment effort, lack of IPv4, IPv6 feature parity is still a big one. There's just things that you are used to seeing in IPv4 that maybe aren't quite there yet with IPv6. We've seen things like ACLs aren't fully developed, or some of the features in certain protocol, routing protocols aren't fully developed. There's little things you run into along the way, things that aren't documented in an RFC, but maybe were secret sauce from your vendor or devices or whatever. So you don't find that out until you actually start using it in your environment, so do that early. Vendors are not eating their own dog food. And what we mean by that is We saw so many cases where we'd get a product from the vendor. It had been fully tested, fully supports IPv6, went through their quality assurance, and so they guaranteed that it was going to support v6. We put it in our network, and it just falls apart. Very basic things. And we would ask them, why did you not see this in your own network? And their response usually was, well, we don't use IPv6 in our network. It's just you guys that are asking for it. And we said, that is wrong. You must use this in your own network. You should be living on it and seeing how well it works. And that's, as some of the vendors have started to do that, that's really been borne out. We've seen over and over again, they said, oh, we started using it, and we saw these things we never saw before. Now we understand, and so they're a lot better about that. Another thing you'll run into, if you have Windows systems in your network, there's a thing called Internet Connection Sharing that is a feature in Microsoft products. And sometimes if you have people that are travelers or whatever, they'll bring their laptop in and it has ICS turned on. Well, if you're also doing IPv6, it has this bad side effect of it becomes an IPv6 router. And router is automatically configured, your default router, because there's a router advertisement that goes to the network and all the hosts learn who the router is. Well, suddenly you'll see one of these Windows machines come in, it's a laptop, it's got ICS turned on, the guy plugs it in, IPv6, he becomes the router, suddenly all the traffic on that subnet goes to that person, and everybody else loses connectivity. Very, very common problem, and there are some workarounds to that, but it's something you'll run into. Next, privacy addresses. If you want stable addresses in your enterprise environment, stable, predictable, never changes, then you're not going to like privacy addresses, and you can read about them in RFC 4941. And so what we have to do is we have to go around to all our Windows machines and other machines and disable that with a registry setting. And it's kind of a pain because you can't do it centrally. And so it's a lot of extra hand-holding. A lot of clients don't support DHCP-v6 yet. So if you wanted to do DHCP, Windows XP doesn't support it. Certain smartphones don't support it. So you'll have to make sure that you have a way to handle that. And usually stateless auto-configuration works fine. Network management over v6 is not quite there, and I got a slide on that. And then after you run dual stack a while, you say, boy, this is added complexity. I want to get rid of IPv4. And we've been at that state for many years and are looking for ways to turn off IPv4, and it's just something you'll run into. People ask me, so if there's no near-term benefit to IPv6, is there any benefit at all today? And actually there is. And here's the things I've discovered. Addressing alone, because of the large address space, is huge. There's things that make life so much easier and a lot of things possible that weren't possible before. So you can better map the subnets to reality. You can better align with security topology, simplifying your ACLs. And it's easier because you don't have to think about, do I use a /27 for this subnet, or a 26, or a 22? How many hosts are in that subnet? You never have to ask that question again because the subnet is a /64. And is it big enough for all your hosts? Wow, you can fit the entire today's internet in a subnet if you did flat addressing. So yes, it's enough because it can hold the entire internet today. So one answer, /64, and you're done. So you don't have to think about that. And then once you see, oh, I've got lots of bits to play with, if there's certain things like I want to have an ACL allow engineering into a certain set of networks but not let the administrative people get into other things or vice versa, well, you can set some bits that just indicate that, and then instead of ACLs that are very complex, they only have to look at a couple of bits. And so ACL tables get much smaller. There's sparse addressing, so it's a lot harder for adversaries to scan the networks and try to find everything or enumerate everything. You never have to worry about growing a subnet. It's like, oh, I had a class C and now I have more than 256 hosts. Now I have to go to a /23 or /22 and change the mask. Those days are gone. It's done. You have auto configuration. You have just a plug and play environment. It's really great with stateless address auto configuration. You have a universal subnet size, so there's no surprises, no operator confusion, no bit map. Those days are all gone. Some cases you can end up with shorter addresses. At home, you don't have to use NAT anymore. Everything gets an address. Link local is implemented on every interface. You don't have to wait for a failure of the network for it to give you a 169.254 address like in the v4 days. It's just there. You can rely on it. So the zero-conf stuff, you can rely on it being there. And if you have a simple network like that, zero configuration just works nice because you can rely on link local. Multicast is a lot simpler. If you've done multicast in IPv4 and have worried about multiple PIM domains and running MSDP and a lot of those very complex protocols, it's very simple now because you can embed the rendezvous point in the group address, and makes it a lot simpler. And MSDP is gone, which is great. Mobile IP is really much, much cleaner in v6, so there's a lot of hope there. Because in v4 it was so complex that almost nobody ever actually ran it. So I mentioned getting rid of IPv4. So what's it like playing with IPv6 only environments where there is no IPv4? And you would think that this would just work. If you've been running dual stack, then just turn off IPv4 and things should just work. Of course, you can only talk to the other IPv6 things, but that's sort of the motivation. Also, if you're a pioneer and you want to do some research and see if this actually works, that might be a new reason. But for a lot of us, it's just dual stack is old and we want to get rid of IPv4. So what are the things you learn? The one place we started already 4 or 5 years ago was our management network is a separate security domain, doesn't talk to the outside, so I don't have to do any routing. So I could make it IPv6 only because I'm only talking to the devices that I control. Could we turn off IPv4, and then how well do things operate? What we found back then is very few devices could be managed over IPv6. You had to have IPv4. But you don't learn what's missing or broken until you try it in production. And we made ourselves remove the training wheels. We actually turned off IPv4 in the routers, in the devices, as best we could, and to see what would break. What would we no longer be able to do? And we're still learning from that. But the other thing is when we would find something missing and we'd go to the vendor saying, hey, you don't support this particular feature, they said, oh, that's an enhancement request. You know, we might get to it in 12 to 18 months. Sometimes it has taken up to 4 years. So it was important to us to try this, discover them early so that by now some of these things are resolved, and we've made a lot of progress there. Here's a chart that I keep. Year and a half ago, I was tracking some of the major router switch vendors, at least ones we use in our environment. And you can see there was a lot of red, especially some vendors. And then now it's changed. A lot of the major stuff like SSH, HTTPS, DNS, syslog, and so forth, that's pretty much all resolved at this point. The vendor there at the top that had a lot of red, this was an effective chart because after they saw that, they didn't like this because they looked worse than the other vendors. And so there was a lot of effort to fix that, and you can see that they are now one of the best. There's new things like the last couple of columns, things we ran into later that were just missing, where you couldn't do it on IPv6, feature parity issues. And so this is a moving target, but the idea is we want to change this to all green so that by time you all get around to try some of this, that it hopefully will be all green and it'll just work and you can run an IPv6 only network management environment. Here's an example bug that we found. This is a case where we, in one of the products, actually turned off IPv4, removed IPv4 addresses from a layer 2 switch. And suddenly we had broadcast storms like crazy because they were kind of ARPing for everything time they saw a subnet broadcast, because they thought they were on all subnets rather than the IPv4 address assigned to the management interface. And so it's just brokenness that nobody saw because it was never tested before. And I think we're going to see a lot more of this in the future because nobody's thought about running things with IPv4 turned off. They thought about dual stack or they thought about IPv4 only, but none of this has been tested. So that was kind of a surprise. We thought it would have just worked, and so we're seeing this all over the place. Another example was where we had a network with only IPv6. Nothing else turned on, just for some of our users. The A bit was enabled, had Slack. M&O bits were enabled for DHCP. And we looked at many operating systems to see how they would behave. And this was Windows 7, Mac OS X, Linux, all the distributions, FreeBSD, iPhones, iPads, Androids, everything we get our hands on. First thing was anything without a DHCP-v6 client wouldn't get a DNS address. So that's Windows XP, Mac OS X before Lion, Android still today. So that was one of the early discoveries. But there was this other thing that was kind of weird. In Mac OS X Lion, You could browse okay with Safari, but Chrome and Firefox would hang. And as we looked at what was going on underneath, it was kind of like Happy Eyeballs wasn't working. And we saw, if we did a TCP dump, it was like doing all these ARPs. And if you study it, it's because they did not have an IPv4 address, they went into this state where they assigned a link local address for IPv4, 169.254. And then there's this other thing, if you know, which I didn't know about until I went back and read the RFC. There's this notion of ARP for everything, because if you don't have any configuration, what they wanted to do was you sort of ARP for everything, and you'd have a proxy ARP router out there that would hear these and would actually get you routed. So it was part of the zero configuration notion. So these devices all end up thinking that they have IPv4 connectivity when it really isn't there. And so they actually try to connect, and you see all this brokenness. And a lot of other OSs have the same problem. We're going to need to go back and either fix Happy Eyeballs or use some other tricks to make it think it's got an IPv4 network, but not really do anything with it. So it's one of those things nobody thought about. We don't have an answer yet. We're looking for answers. And so what we're having to do to make things even work nicely is go into Lion or other operating systems. And if it's got the knob that says turn off IPv4, you can do that, and that helps a lot, because then it doesn't do this ARP for everything thing and similar tests. So I think that's the last slide. But it kind of gives you a feeling for, if you haven't started yet or don't know anything about IPv6, here's how we got here. Here's the benefits. Here's why you need to do it now. And I hope you are all deploying something today, because it is becoming urgent. It's almost becoming a crisis. We really need to do something very, very soon. But if you're as far, advanced as to the point of actually turning off IPv4, there's some things you're going to run into, but there's people working on the problem. So hopefully by the time you actually get around to trying this, these bugs will all be fixed. So I think that's it. And you can contact me at that address if you have any other questions. And thank you.
Thank you. Are there any questions?
I'm not quite up to date with IPv6 developments right now, but for a long time there was imposed list. There was a limit imposed on the number of autonomous systems. It was 1004. It was together with introducing IPv6. There was some statement that the number of ASs should be so limited. Is this still true? Or
Number of ASs?
autonomous systems.
I don't know of any limitation. I mean, other than the 65,000.
There were some meetings where this thing was discussed or announced, and so it's there is no such thing.
Well, originally it was 2 bytes, but it's been extended to 4 bytes for ASNs. So I don't know that that's a limitation anymore.
So the amount of ASs as it is now for IPv4 will be the same as for IPv6.
Right.
So we can keep our AS.
Oh yeah.
There is no limit.
Yeah, because my AS number, I was one of the early ones. I'm number 22, and it works just fine on IPv6. But even ones that have the later ones, they work fine as well. You don't have to change ASNs.